So like I said, this will be the last segment we do tonight, and then we'll head home, or if you want to stay for the review session, that's fine too. So skipping to chapter 16 because we can, and this might help you with some of your photo projects. Maybe, maybe not. Remember, if you're doing a photo project, you can do clouds, like the 10 different cloud types. You do different clouds, but they have to be unique clouds. So you can have stratus cloud, a cumulus cloud. Those are two different things of your 10. All right. So we're going to focus on just the form of electromagnetic radiation called visible light, okay? And it's going to make these cool different things in the atmosphere that you're already kind of familiar with. And these interesting things that we see happen are either due to reflection, refraction, diffraction, or interference. And we'll talk about what each one of those are. Actually, just the first two especially. I don't think we're really going to do much with diffraction or interference. But reflection looks like a mirror, right? There's a slight difference between this sort of reflection and the other sort of reflection I'm going to show you. This is where you have a nice flat mirror, and basically you can anticipate where your reflection is going to go. The angle of incidence is equal to the angle of reflection. So this actually, again, is reflection, but it's more of a kind of a scattered sort of thing, an irregular surface. So that leads us to, and by the way, you can get this, like the slide says, if you take aluminum foil that's flat, if you crumble it up and try to flatten it out, you'll see these kind of kinks in there. So this is actually kind of the second case where you kind of have a little bit of random scattering with this kind of uneven water here. So this doesn't really have a name, but it almost looks like you can see, and I know some folks in here have talked about coronas. It almost looks like you can kind of see a corona around the sun, but I'm not sure that's what that is. But this actually band of light becomes from kind of that kind of unusual scattering of the sunlight off of the water. So that was reflection. There's too many R's. This is refraction, okay? So refraction occurs when light leaves one medium and goes into another medium. So here we see light going from air to water, light going from air to water. Okay? In this case, you actually are seeing refraction, by the way, is a bending of the light. So instead of the light going straight like this, the light actually is bent. That's refraction. Why? Because there's two different mediums. All a medium is basically the stuff that light's traveling through. Okay, so light will be bent like that. Notice that if the light is actually perpendicular to the interfaces of the two medium, there's no refraction. Okay, so light is bent. Now, light is bent because it actually travels at different speeds in air than it does in glass. And I was thinking about this today. I'm like, because you're like, oh, speed of light, it's blah, blah, blah. And you can usually rattle off, it's like 3.00, I don't know, times 10 to the 6th kilometers per second or something. Speed of light, it goes this fast. Well, that's in a vacuum. Okay, so if you mess it up and it's not, light isn't traveling in a vacuum, but if it's traveling in air, traveling in glass, then actually it travels different speeds. There's this property of medium called the refractive index, refractive indices of material that light can travel through. And that actually, it goes back to the speed of light being slower. So those interphases, when light travels from one medium into another medium, just kind of like this is showing you a car traveling on nice, smooth kind of wooden floor versus a car, that same little toy car traveling on carpet. It's going to change speed. Why? Because there's more friction with the carpet, right? So it's going to slow down, but like this slide kind of tells you, kind of by the angle of the car, can you see where this tire is going to, this right tire is going to go first, right? And so it's going to slow down. Meanwhile, the left tire keeps going as fast as it was with a smooth surface. So that's actually, and cars will do this. And this is why the light does this. It changes speeds in different mediums. Okay, so actually it veers this way because it's hitting a different surface and going to slow down. So light is bent. Light is refracted. Here in a minute, we're going to switch gears and talk about actually how prisms refract light and you get different colors. But for now, I'm just going to stick with basically, we're not getting different colors. Basically, the color of the light is all kind of refracted all at once. So you have to kind of study it. You're like, that just looks like a bowl of water with a colored pencil in it, right? Okay, but if you look at it closely, you're like, okay, it does look like the colored pencil is disjointed. And that's because the light that's coming out from the pencil, this is how I think of it, the light that's coming out from the pencil, for us to see it, actually is traveling through water and then traveling through air. Okay? The light we see from the pencil itself, just air. The light from the part of the pencil that's in the water, water and then air. And thus the bending. Okay, it happens all the time if you go swimming and you can kind of, put your feet in the water and you can kind of see it looks like your limbs are disjointed. So water refracts, light traveling from water to air will be refracted. And refraction is the bending of light. Okay. So this one, what I think I'd like to emphasize is this actually allows us to see, I'll put it at the bottom here, we can see the sun below the horizon because of this effect. And I think this slide kind of exaggerates it. Okay? But notice that here they're saying that the sun is really here, but this is where the position that the sun appears to be, and it's because the light coming from the sun is refracted. So I said refraction happens when light travels between different mediums. Okay, here's the different mediums. Basically, you guys told me if you climb a mountain, the air gets thinner, right? That's one medium, thin air. Down here, thick air, okay? That's your two mediums, and that's what's actually, light will travel different speeds, and it will be refracted like this. So the refraction, I'll switch to a purple pencil maybe. The refraction, purple. The refraction is here. Can you kind of see the bending? It's kind of a subtle thing. And the reason the sun appears here is, I usually say this is like its last known trajectory is like this. So its last angle to us is there, and that's why it appears to be located up here. Bends, last known trajectory. All sorts of kind of neat little mind games played with our eyes because of that. Okay, so there's two types of mirages, and mirages are created by refraction. So refraction is because the light must be going through two different mediums. But the things that both of these mirages have in common is the two mediums aren't because of thick or thin air. The two mediums are because of the temperature of the air. It's all about air temperature now, not, like I said, thick or thin air. We'll start with what's called the inferior mirage, and then we'll talk about the superior mirage. Up here, if you want to, inferior mirage, and you'll see why this is, I would equate this with a puddle in the road. Okay, that's an inferior mirage. Okay, basically you're driving down the highway and it looks like there's some sort of liquid in front of you. And I'm going to try to convince you that that's because of the temperature differences. Okay, and basically you are seeing kind of the trees down below the horizon. So an inferior mirage. So this is the puddle in the road sort of thing. This is an inferior mirage. So I said it was about temperature. Both inferior and superior mirages are about temperature. The inferior mirage happens because you have what we call a steep temperature gradient. That just means the temperature changes really quickly. It's really hot on the sand surface, and the air cools down quickly. Okay? You're driving down the road. It's really hot on your pavement, and the air cools down quickly. Okay, so that's able to bend light, and here's how it bends light. So what I like to say is you basically see this tree in two locations. This palm tree, which some of us might see on spring break, I don't know. Okay, so you see this palm tree up here because of this light coming directly to the observer. Okay, you see that whole tree. You see the trunk of the tree, blah, 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 blah. The other direction that that light from that tree is going is I guess I should say in all directions. Some of that light is not coming directly for you. Some of it's going this way, some of it's going this way, some of it's going this way. The light that is actually going down, okay, is bent, is refracted. Let me choose the orange color. This is actually the refraction part. Okay, it dips down and back up. So again, like we did with sun's position, the last known trajectory, okay, of that light that was refracted is up here. We bend it back down, and the top of the tree, we see the top of the tree here, and we see another top of the tree down here. Now, I've never seen a palm tree like that, okay? But it's the same phenomenon that happens when you're driving down the road and you see an inferior mirage. So the two things about inferior mirages, does it look upside down? Okay, so that's one thing about it. It will be upside down. And the other thing, to compare it to the other type of mirage I need to talk about, is that it is below the horizon. Okay, so it'll be underneath the horizon. So basically, that's how that works. An inferior mirage. So a superior mirage, I really can't relate to this. But a superior mirage, I'll go ahead and underline it here, you are actually going to see the object hover above the horizon, okay, and it will not be inverted. But what creates this hovering object actually has to do with temperature again, and it specifically is a temperature inversion that's in place. So a pocket of warm air has kind of snuck in over your cool air. So the object will appear above the horizon, and it will not be inverted. Although some pictures, I swear I see, they look like they're inverted. All right, so meet the hovering ship, superior mirage. Let's look for the temperature inversion that must have created it. So we know that normally as you go up in the troposphere, it's supposed to get colder and colder and colder. Well, here you go. There is your temperature inversion. Okay? And that temperature inversion extends through, you know, kind of horizontally like that. So that means that we will see the ship where it is. Okay? We'll see it there at its normal location. But the light that actually going this way instead of just going and leaving, that light will be bent. Okay? And that bent light will reach us here, and its last known trajectory is here. So actually you'll see a second image of it off in the distance. Now this is a figure, so I've actually got the real photograph to show you here in a minute of a superior mirage. So again, you see it above the horizon like the previous slide said, and it will not be upside down. Inferior mirage. Yep. And if you look closely, you can actually kind of see, you know, they're not palm trees, but for instance, you see this green thing is actually kind of inverted kind of down there. Can you see it in the puddle? I guess more closer to home, you see this vehicle. Okay, so you're actually seeing the image down underneath there. So here's the superior mirage. And to me, like I said, and I've looked at several of these, this to me almost looks like it's inverted. The real, they look like mountain ranges to me. The real mountain ranges would be here, okay, kind of along here. And then this would be the superior mirage.
Where are you right
down here. Where am I writing at? Do you want me to make my arrows bigger?
No, I can see it now.
Yeah. It is kind of disorienting. So like this is the sky over here, and this actually is the mountain range, and you kind of see it. So, yeah, I think it's creepy too. All right, so rainbows. Who doesn't love a rainbow, right? So one of the things, and if you're a visual person, this is the way I always think of it. One of the things I want you to know is what are the conditions necessary to see a rainbow? Well, the sun needs to be low on the horizon. Of course, that means sunrise, sunset, rise/set. That's what I mean by low on the horizon. So if we go ahead and make this west over here, then hopefully then in our eastern sky, and this is going to be us standing here, little person again, hopefully in our eastern sky we can see, these are my little liquid water droplets. Okay, so in a minute I'm going to actually show you how the light from the sun actually, if the sun's low on the horizon, actually there's an angle criteria, but that sunlight is going to interact with these liquid water droplets. And honestly, that's quite possible if you figure that you have a storm system. We'll go ahead and make this a storm, cumulonimbus clouds. Storm system that is already traveling east. It's quite possible that you can go ahead and have that set up. We can have rainbows happen in the morning, but it's a little less likely to probably happen when the sun is low on the horizon. So I have finally a video to play for you. Let's see if this plays. I haven't tried it for a while. That's what I get for randomly picking a video. All right, so it can extend 85 degrees is kind of the max. So from side to side, if you see one bit and then the other, where the pot of gold is and the other one.
There is a pot of gold?
No, there's no pot of gold.
Damn. Is that proven?
There can be a secondary rainbow above,
You mean
outside
a
the
double
primary
rainbow?
When she
Double
said there was a
rainbow.
rainbow video, that's exactly the video I thought she was going to play.
Dude, that guy was on LSD.
Okay, well, we'll have to talk later. That doesn't sound very scientific either.
This guy was just tripping balls because he saw a double rainbow.
Oh, goodness.
He was excited. That's what I'm like every time I take a picture in this class. For
Yeah.
a photo project.
All right.
Yeah,
Very
that's how
good.
excited I get about it.
Okay. Good. Okay, so and maybe you already know this, but the colors, and I'm not going to choose the different colored things because that'd take me too long. But if that's the primary rainbow, then from the inner to the outer color, it's going to be, we talked about the Roy G. Biv, the red is going to be on the outside. So it's going to go red, orange, yellow, Roy, green, blue, indigo, violet. And I'll do a number 1 with the circle for that's my primary rainbow. Roy G. Biv. Okay. Then if there is a secondary rainbow, it will be outside and it will connect up the reds. So if this is my secondary rainbow, it goes the other way. Red, orange, yellow, green, blue, indigo, violet. Going out that way. Okay, so anybody in here seen a double rainbow?
On video.
I know, I've seen one. I live around the Mississippi River, and right
That's
in front of
right.
that it happens all the time.
Oh, that is so
It cracks
cool.
off the water.
That would be beautiful. Pictures.
That one's really vibrant.
Yeah, that one's vibrant.
I think it's photoshopped.
I don't know. That's what I wonder.
Potentially.
That's very pretty, though.
Oh, yeah, that is from the book.
Okay. So refraction of the pencil, we saw basically all colors were bent the same. Okay, refraction of the pencil occurred because light was going from the liquid water to the air. It was bent. So refraction also, though, can kind of be selective for the different colors of white light. Okay, a prism, you probably all played with prisms before. Basically, it makes use of the fact that because of the shape of the glass, when white light comes through, depending upon the wavelength, the Roy G bit, red's the longest wavelength, violet's the shortest wavelength. Depending upon the wavelength of all those components that's coming through, the red will be bent the least and the violet will be bent the most. So basically it takes what's a mixture and it goes ahead and separates it out. And Newton was the first one to see, and this is refraction too. It's just, but it's basically not refracting all colors of light the same. Okay, and it has to do with the geometry of the prism. Okay, well, actually, we know that kind of the scenario I set up with the sun over here and the little liquid water droplets over here, and this is where you're going to see the rainbow over here and the liquid water droplets. Well, we know rainbows are basically white light that's basically been separated. Light from the sun has been broken out into its components, just kind of like a prism does, okay, to white light. So I'm going to show you in a minute a picture of a little liquid water droplet, and you're going to see basically when water, as long as the sun's low on the horizon, when white light enters that little water droplet, it's actually broken out into its different components. Okay, the red is bent the least and the violet is bent the most. For every little liquid water droplet does that in unison. How wonderful. And then it bounces off the back of the water droplet back out, okay, to see a rainbow up there. Okay, so this actually was what I was talking about. Okay, isn't that, if this is drawn to scale, this is just very scary. Little liquid water droplet, and there's your little person. Okay, but anyway, so light comes into the little liquid water droplets, okay, and it is broken out into its components. Can you kind of see it breaking out into, the red is bent the least and the violet is bent the most. Then the back of the water droplet actually acts as a mirror, like an internal reflection. It comes back out, and it creates the image we see as a rainbow. So it's pretty cool, almost like holographic, right? Okay, so, and this actually is on your test. The question goes something like, for that secondary rainbow, which you may or may not see, which is above the primary rainbow, if that's the case, well, what's happening in this case? And what's happening is you get one more reflection, okay? So notice here we have the sun's rays coming in. We have refraction, breaking it out into its components. The red light is bent the least, the violet light is bent the most. It bounces once, and it bounces a second time. Okay, so the answer to that question actually is that it reflects twice. For your
Which also
secondary.
explains why it's harder to see, because it probably loses some strength in that second.
Yeah, I buy that. That seems reasonable to me too. I like that idea. So here, I don't know if it's photoshopped or not, but
What does it say down the bottom?
very much.
Pearson navigation.
Yeah,
I can't-
this
If
came-
it's from the textbook, I doubt it's, I can't read that far, man. Anyways,
It's Pearson 2013.
can you read it from there?
Yeah, but.
Maybe my eyes is real bad. I would assume that if it's from the textbook, it's probably not.
But you see that the red are in common, okay, so the innermost of the primary is violet and it ends with red, and then the secondary begins with red and ends with violet. That's very pretty. All right. Now we just kind of finishing up with kind of a series of, oh, that's cool in the sky, and what do you call that? So you may have seen these circle things around either the sun or the moon, and sometimes they can have some color to them, but these are differentiated from the other thing I want to tell you by the fact that these actually have kind of a nice edge. There's a gap between the end of the halo and there's a space before you get to either the sun or the moon. The other thing, and this actually is going to be on your test, so I'm going to show you a picture of a halo, but halos are caused by the presence of ice crystals. Okay, so you're going to want to know that for your test. And so you're looking for a cloud that has ice crystals, so it's probably upper elevation, and something that's kind of nice and wispy. So cirrus clouds or cirrostratus clouds would be great for this, creating this effect. So halos, some couple of halos here. Okay, there's a halo around the sun, there's a halo around the moon, and you can kind of see a tinge of a color to them. And it's by light refracting from that particular type of ice crystal. So those were halos. Here is an object called the sundog. Anybody in here seen a sundog?
The
Or?
picture that you showed your picture at the beginning.
Yeah, sundogs, that's right. Exactly. And these are also caused by crystals. Where is it? Okay, ice crystals. Okay, high-level wispy clouds. And if you have to describe it on a test, hint, hint, you know, if you just go ahead and kind of say they're like little mini rainbows on either side of the sun, that would be great. These are, sundogs are kind of like rainbows in that the sun has to be low on the horizon too. Coronas and halos, the sun doesn't have to be low on the horizon. Sundogs and rainbows, the sun does have to be low on the horizon. I don't think this is a great picture. I thought the one that I brought earlier was better. But the thing in the middle is the sun, and kind of on either side are the pair of sundogs. Sometimes, actually, I've seen it, and maybe you have too before, but you can see if these are the sundogs, you can actually kind of see an arc that almost kind of looks like a halo around it.
That one's really big too.
It is big.
So, go back to that sundial quick.
Okay.
I have a picture that I thought was one, but
Doesn't match up?
no, I'm not going.
Okay. Okay, so another object is a sun pillar, and this is also ice crystals, in case you're asked on the test about it. Okay, and just like a pillar is kind of a vertical sort of thing that holds the ceiling up, okay, that's kind of what these look like. So you have the sun here, and you have kind of a pillar of light. I've actually think I've seen a pillar going both ways, not just up or down. So here's an example of a sun pillar going up vertically. You got one of those? No. Okay. Oh yeah, nice.
Okay.
I'm liking it. Sun pillar. Cool. Very good. And then there's a glory, which actually is, I don't know if you can see it, but down here is the glory. And you need to have the sun behind you. It's kind of like a circular rainbow. Yeah, circular rainbow. We talked about these earlier. I'll try to see if I can find one of my favorite websites or a couple of websites that actually are just filled with pictures of this stuff. So this actually mentions too that you can see, these can be seen, and when I get to that website, you'll see that looking out the window from an airplane down into clouds, if the sun is over here, sometimes you can see these circular rainbows too. Okay, and last but not least is a corona. I used to make a big deal of the difference between a halo and a corona, but a corona is not ice crystals. And by the way, I don't know if you saw, let me go back. Yeah. Go back to the glory. They are caused by, let's make it obvious, they're caused by liquid water droplets, like a rainbow, okay? Suspended liquid particles. Corona are also caused by, see the word liquid? By suspended liquid particles. And the thing about a corona, they can also be around the moon or the sun, but they touch the moon or the sun. Okay, and they're more whitish. They don't usually have, they can have some color to them too. And here are a couple pictures of corona. This is a corona around the moon, and this is a corona around the sun, which I've never really seen it look like this around the sun.
I thought the only time you really ever saw a corona around the sun was during the solar eclipse.
That's when you see the chromosphere around the sun, probably. But, close. All right. So we'll take a short break. That's all I had for tonight, right? And so two chapters will be due next week. That seem right? Unless you didn't bring one today. Then there'll be 3. Okay, so see you next week, and then we'll just pick up with Unit 3.
Does anybody want to take pizza home with them?